Welcome to an introduction to the parallelogram method of vector addition. You'll recall that forces are vector quantities, and therefore they can be represented by vector arrows in diagrams or models. Remember that the arrows should indicate both the magnitude or size of the force to some sort of scale, so the magnitude is indicated by the length. And the vector arrows should also point in the direction that the force is acting. On any given object, multiple forces could be acting at the same time. When you first draw vector arrows, place their tails on the object to which they are being applied. So let's include an object here. And now let's draw two vector arrows. So you see vector A and vector B. These two vectors happen to be at right angles, and B is larger. Now, to find the net force or resultant, we are going to use the parallelogram method in this video, but just a quick reminder, the other graphical method that we learned was the tail to tip method. In the tail to tip method, we'll pick one of the vectors and move it over so that its tail is touching the arrowhead tip of the other. So let's pick on B and move it. And now the resultant is drawn from the origin, the original tails, to the last arrowhead tip. So there is the resultant of these two vectors. That was the tail to tip method. Now we'll see the parallelogram method, which is very similar in some respects. First, you do exactly the same thing that you did with the tail to tip, except that this time, instead of erasing the B vector, we'll leave it there. And we'll do the same thing with the A vector. We'll move it so that its tail is touching the tip of B. And what we formed here is called a parallelogram. In this particular case, because the original vectors were at right angles, we formed a rectangle. But a parallelogram is any four-sided figures in which the opposite sides are parallel. It doesn't have to be a square or a rectangle. The resultant is drawn from the original object, which is where the tails are, to the place where the two arrowheads are touching. So if you draw that vector, what you see now is that all the tails are touching in one place and all the arrowheads are touching in another place. So that is the parallelogram method of vector addition. Now the parallelogram method works very well with vectors that are not at right angles. It does have a drawback in that it can only work with two vectors at a time. The tail to tip method can work with multiple vectors as long as you add them one at a time. But the parallelogram method, you can do that, it just takes a while. But it has another power that I'll bring up later in the video, and you'll understand why we are learning this method. Let's draw that object again, and this time let's draw that as a vector and that as a vector. So now we have two vectors that are not at right angles, but we can still construct a parallelogram from them. Let's pick one vector up and move it so that its tail is touching the tip of the other. And now we'll pick up the blue one and move it so that its tail is touching the tip. We'll draw the resultants from the place where the tails are touching to where the arrowheads are touching, like so. So it's the diagonal of that parallelogram. There's your resultant. Now, we didn't include any numbers here, but in an actual problem, these arrows will be drawn to scale, and we can now measure the length of this resultant and convert it to a magnitude of, say, a force vector. We could also measure its angle. Let's try it again with vectors that are more widely spaced. So we'll draw one in this direction and then one in the opposite direction like so. Pick up the red one and move it, and pick up the blue one and move it. So again, what we're doing is the original vectors are still there, but we're drawing copies of them. We just move them over so they're in the same direction and the same length, and we put their tail at the tip of the opposite or other vector, constructing a four-sided parallelogram. The resultant is from the object, the origin, where all the tails are meeting, to where the arrowheads are meeting. Here's your resultant. If those two original vectors represented two forces acting on an object at the same time, the resultant shows you the direction that the object would be forced by the net force. So the resultant would be the net force in this case. So here's a practical example of the parallelogram method or rule at work. Here's Nellie Newton suspended on a ring from two strands of rope that are attached to the ceiling. It also has two spring scales there. And the question is, what would those spring scales read? Would the tension in the actual rope be greater or less than the tension if you had, say, two ropes that were hanging straight up and down? So we can look at this as if it is a parallelogram. First, I want to make sure you understand we're going to draw vector arrows on top of this diagram, but the vector arrows do not actually represent the ropes. They represent the forces. Okay? Ropes are real objects. Vector arrows are not real. They are graphical representations of reality. So the reason I'm pointing that out is that the vector arrows along the angles of the rope will not be the length of the rope. The actual tension is in that rope all along the length, but our graph will be drawn to scale. So what we want to know is, how long should these vector arrows be? So if we call those the two vector arrows, then we move one. I should have left one behind for you to see on the opposite rope, but let's just pretend like it's still there. Now we can draw an upward resultant like so. That resultant would actually be the same as Nellie's weight. Since she's hanging suspended, that means she's at rest, she's not moving. The upward forces must combine to equal the downward forces, which is her weight. So the question is, though, what is the tension in those two ropes? Well, it would have been determined from the length of those two vector arrows. And if you add those two vector arrows together, you can see they are longer than the yellow arrow. So the tension is actually greater than half. Each rope would have greater than half of her weight. If you had two ropes that were hanging straight down, then they would equal half of her weight. What I'm trying to say is, if you put ropes at an angle, then the tension goes up. So again, what we tried to show there was we can look at a real life situation and try to imagine what it would be like if we sort of represented that with a graph, and then from the graph we can construct a parallelogram and look at the resultant. And each vector red dashed arrow is more than half the length of the solid red arrow. Whereas if this were just two ropes hanging straight down, they would only be half, because they would have to add up to the weight of Nellie. So one reason why it's important to learn the parallelogram method is that you can apply it in reverse. Then we could do things like determine the actual tension in each rope if we knew Nellie's weight. So let's say, what is the tension in the left and right rope? Well, let's represent Nellie's weight by a downward vector arrow. We'll color it green here. The combination of those two ropes must be holding Nellie up with an equal force. So we'll draw an equal size vector arrow in the opposite direction. We're not going to make them touch here because we're not actually adding them together. So the resultant is just a representation of the combination of the actual forces in the two ropes, the tension in the two ropes. What we can now do is sort of do the parallelogram method in reverse. We can imagine that that resultant is a diagonal of a parallelogram. So we'll put some dashed lines here down to the actual ropes and draw ourselves a parallelogram. So these lines are not arbitrary. Let me move them just to show you that the vector arrows I've drawn on top of the ropes and the dashed arrows are aligned. Okay? So you can see that's how we would have drawn it if we were going forward. And what we did was we went in reverse. Okay? So we drew it like this. And now we could, if we wanted to, measure those two tensions, how long they are, and convert them using a scale. And again, I think it's pretty easy to see that both of those tensions are pretty close, almost as long as the total resultant. So in other words, the tension in the rope here is very high on either end. It's more than half of her weight. If you apply this parallelogram in reverse, you could find the tension in ropes for all kinds of other angles. And one interesting result is that you would find that as long as those two ropes are not parallel, hanging straight up and down, they're always going to be more than half of her weight. And the larger the angle, the more that tension is going to increase. Here's a large angle, and you can look how long those vector arrows are. In fact, they are now longer than her weight. So the tension has actually gone above her weight. I know you may not think that's physically possible, but this is, in fact, what happens. Each rope is trying to hold up more than her weight. In fact, if you strung a clothesline up, you might find that you could hang straight up and down from it, but if you tried to stretch it very, very tight, then it might actually exceed its breaking point. You can use this parallelogram method for odd angles, so the rope does not have to be at the same angle for each side. For this particular diagram, you can see that with the steeper angle on the right, you have a larger vector arrow after you draw the parallelogram. So there's actually more tension on one side, the right side, than the other. Here's a thought question for you. Let's say that you were at a swing set watching children on a swing, and you see one swing that has parallel ropes and another one with non-parallel ropes. Which of those two children are most likely to break one of those ropes? Well, the one that's parallel is going to have half of the child's weight in each rope. The one that's non-parallel is going to have more than half of her weight. So the one on the right is going to have greater tension in each rope. Here's another thought question. Consider what would happen if you suspended a 10 Newton object, or any amount of weight, along a very tightly stretched wire like a guitar string. Is it possible for that string to remain perfectly horizontal without some sort of sag in the middle? Let's figure it out. You probably know from real life that if you hang something from a rope, it sags. And there's a very good reason for that. The weight is a downward force. In order to hang, it must have an opposite force in the opposite direction. And that force can only come as the result of the addition of two forces in the rope, one on the right and one on the left. Those forces must be along the actual rope. So if we do the parallelogram method in reverse, you can see there's a very large tension in both sides. But you cannot get that resultant without a parallelogram. If you did not have a parallelogram there with a diagonal in the middle, then there would be nothing to oppose the weight hanging down, and so that weight would actually be going in the direction of the arrow. In other words, it would be falling. There is no other choice. If that weight is suspended, which means it's not moving, there has to be an opposing force to the weight. So I hope that you can see that this parallelogram method is useful in figuring out certain types of problems. You simply move the two vectors so that their tails touch the arrowheads of the opposite vector, and then draw a resultant from the origin to the final place where both arrowheads are touching. And then if we had those drawn to scale, you could measure them and determine the actual magnitude and the direction by measuring it with a protractor.